Okay, I'd like to set up a kind of a quick introduction to this idea of node-based or parametric programming. Um, I don't want to formulate too many rigid ideas about what it is because it happens to be so many different things. But we'll start out with this kind of, commonly thought of idea when we talk about, computational design and complex fabrication. So we have a curvilinear space with a lot of parts and pieces, and we wonder how we put it all together. And this is a nice podcast from Chris Sharples, a senior principal at Shop Architects, one of the founders. He talks about this idea of direct design to fabrication. And they were very early in the ideas of how to create these complex ideas in fabricatable ways, or ways to communicate to the people that would be building them. And I think that's one of the strong components about this idea of digital and computational design, this ability to translate our ideas into things that can be made. And so here we have big architects. This is an art installation. I think it's called the Serpentine, but I thought it was an interesting visual here because we just finished the idea of making a panelized system or a unitized system, and these are all boxes. In this case, they're applied to a curvilinear surface, and obviously this would be a nightmare to conceive erecting without the aid of computational design. And their firm is really famous for that idea of, or strong in that idea of using computational design. And it can be in nuances within construction. It doesn't have to be the very defining core, but it can be the idea of how a facade might articulate in a certain area, and then all the complexities that come along with the idea of understanding how that would be rendered, modeled, and eventually fabricated. Another leader, Nautasis Zaha Hadid, very much an architect who used to refer to math as her form of sketching, creating all kinds of beautiful architecture and form. Many projects just being completed quite a while after her passing. So I would really invite you, if you're interested, as a female architect. She is one of the leaders in the field, not just because she's female, but I mean that is one way to relate to her significance in a field that's strongly dominated by men. I wanted to touch base on the idea that we're going to be looking at this, but there are many people that I've used as resources to learn this information. So we've talked about the architects that are practicing it, but on the other side, there are people who are teaching it. Zach Cron, who works for Autodesk now, I believe, has created a lot of very practical introductions to these kind of computational techniques. So this is hyperlinked. It'll take you to his site for a lot of really informative educational components. Jeremy Rowe, an instructor, I think at North Carolina University, a whole host of beautiful resources that he's created. And our original introduction, just a step where we're going through with this in computer viz, was to, and some of you may have had this and some of you may have not, but I'm introducing it now again just to help familiarize us with it. But in computer viz, one of the last projects we do is to look at computational design. So in this case, we're taking panels. We're creating a panel width, a panel thickness, as you can see here. And we have an attractor, a point out in space. And we make a relationship between these panels that we build in an array that we set up. I can't point out exactly where the array gets built here. It's here. The points by coordinates. So we put a series of numbers in and we come up with an array. We put a panel on it. And then we manipulate it with respect to that point that we're creating out in space by changing its color and or its rotation or any other effect that we might deem worthwhile to experiment with. And this is kind of, maybe a happy happenstance type of mistake that also is an offshoot of being able to just play with numbers and sliders to find out what effects can be created very quickly and efficiently. And they may be the genesis for new ideas and concepts going forward. And obviously, I want to make sure that I kind of punch home the concept that computational design isn't really just limited to form creation. It can help us understand structure, help us to generate secondary structures to go along with our primary elements that we're designing. And then this class will actually look at using parametric design to dynamically load a truss system to observe its deflection with changing support and load conditions, and then be able to visualize the stresses on the members, whether they're in tension and or compression. So I think this is just another exciting opportunity for kind of understanding the math of structure. We can also look at the math of things that aren't working out quite properly or fitting into our system. So what I mean then by that is it could be collision detection with pipes and plumbing. But in this case, it's we're using software to determine on this curvilinear shape that we panelized which panels will fit the flattest and which ones will be out of alignment. And we can apply colors to that idea of those that aren't flat, so we know where we need to put the most amount of attention into our design. So we'll see a lot of representation going forward, especially once we start working with it, with these ideas of parametricism and the kind of facades that we get from it. Probably this is not a parametric facade. There's very little going on to change, and it could be parametric, obviously. I'm not going to eliminate that concept, but this could have been accomplished with relatively traditional geometric techniques. You know, we could have all probably panelized and built these components and done this type of facade. But I want to show you how this can now then move into parametricism, computational design, where we can apply other kinds of effects, changing the nature of form, shape, and color as we translate a panelized system through, you know, a space. And we can assign the effects based on images, of math, of all kinds of relationships that we would find interesting. So I showed you back here about this idea of what could or could not be a parametric facade system with a shading system on it. And now we have a shading system on what is a really very traditional building. It's almost a glass block building. We have some nuances here in its shape. But we have these metal panels now that are articulating almost as if the wind is blowing across the facade. And that's really accomplished, I guess, relatively easily by these mesh panels that are applied to the facade and then articulated according to a mathematical structure that we've created to create that form. And that carries on to the inside and some of the ideas of panelization that happens inside of the building. And this is morphosis. That was morphosis. That was the gate center. I'm sorry. This is the Gates building at Cornell University. So this is actually a close drive from Alfred. And this is the Emerson College in California. This is also morphosis. But now they've taken that same idea and technique. Still, a lot of form is rectilinear and straight and conventional, but then in the inside, kind of like this idea of carving out, and you can almost feel the flow of wind through the interior surface to create a kind of a dynamic effect. So you'll see a lot of examples of this, and I want us, and one of our goals is to be able to start to look at these forms and really kind of understand how they've been mathematically created and the kind of rationale and thinking that goes behind them. And so if curvilinear surfaces are kind of intimidating, there are plenty of applications for computational design in all kinds of ways. And so I'll start with the idea of just looking at the manipulation of flat surfaces and creating kind of pattern systems. In this case, I had the opportunity to create these security screens for rigidized metals. And I had some ideas about a Voronoi pattern that would allow only a certain kind of hole size. And I wanted to create enough randomness so that it looked like there were no repeats in the pattern system. And so I was able to use a really very simple mathematical description about using random seeding, creating a Voronoi pattern. This is a mathematical relationship about how we draw bisecting lines between points. I could offset those points to create the kind of gridded system we want. And I had all the adjustments to create, to vary the number of panels, how thick that offset would be, the size of the panels, the amount of randomness that I wanted to introduce, the curves at where the points intersected, all with a simple definition that led to an output file that looked like this. One of the variations that was added to this that makes it more interesting is these white dots are considered seeding. So I made additional points within the definition, and you'll notice that wherever there were a concentration of points, it caused the pattern to kind of relax or have less divisions in it. Where there are fewer seed points, you'll notice there are more divisions. So I was able to create that sense of random behavior within that grid system. So that was a fun and interesting project, and a nice use of computational design to help assist in that. Computational design can also assist in things that aren't actually structures. So here we have actual structure though, but we also have lighting. The ability to determine color and lighting systems and schemes. And this might be in a relationship where you're building a panel system and working with a lighting designer and trying to coordinate concepts and ideas together. There are a lot of instructional materials available for you if you're strongly interested in this, and I want to point you to a couple of them. One is Mode Lab, where you can, they have the whole primer on using Dynamo, which is the node-based programming system. Lunchbox, they have also a host of resources available to you. If you'll get into checking some of those out, you'll discover that there are a lot of functions that you can use, parametric programming or node-based computational design, to do all kinds of things, like just adding dimensions to Revit room tags. You can do functions that Revit currently doesn't allow by using this programming environment, which is relatively easy to use, to enhance and do tedious tasks that you would just love to be able to automate. When we talk about curvilinear space, though, just one short topic I wanted to introduce, this idea that we're very used to working in XY space, XYZ space. And one of the new introductions that we're going to find, and I thought these were good graphics and I wanted to show them to you right away, is this idea of a UV coordinate system. So now when we're talking about trying to define something on a curvilinear surface as opposed to a rectangular surface, well, we define those as U and V instead of X and Y. And our normal component, which is the vertical axis, is defined as a y coordinate, or in some cases is referred to as the normal vector coming off of any given point on that surface. And when you understand this kind of way we're going to define surfaces going forward, that allows us then to create all of the nodes along that UV surface to create UV divisions that can allow us to grid and eventually panelize those surfaces and work with them in more advanced ways. And so then our reduction to practice of these ideas will be our project this week. And we're going to look at last year's Computer Viz, the final assignment to the students. We're going to do that just to give us a refresher on this, or a learning episode for those who've not done any of this before. So here we have a definition. We have a line that we're going to place on the floor of the building, an imaginary line, and we're going to let that inform the shape of our ceiling system. And I think this is a really a nice introduction to parametric programming. If you don't like the idea of the complex far out surfaces, this is just an idea of a manipulation of ceiling panels, and those effects can be much more dramatic and or sedate depending on how you might envision them. And it's kind of germane right now. After I had done this project this year, this is on the National Mall. So you can see here now we have basically the same concept. We have a ceiling system, which is tubes coming down, responding to what they refer to as a data set. And this is a response to Black Lives Matter and oppression systems, and anyway, it's a sculpture, but it's also an architectural space that gets created, and very much related to the techniques that are used are very much related to the project that we're doing for for this lab. So I hope you'll enjoy it and be able to take something from it.